start with the last talk for today. Thank you, Professor Jedediah Pixley, for accept our invitation. He did his PhD in Rutgers University, and he's director of the Material Center in Rutgers University. And this is exploring the diagram and topological factors. Thank you.
Thank you. So yeah, I'm a physicist. Okay, so fair warning. Surely not a mathematician. But this, I think, topic needs to get a lot of attention from the mathematical community. So maybe I'll inspire some of you to put some rigor where we can figure things out more conceptually and qualitatively. Okay, so I'm going to pose a general question about the structure of phase diagrams of Z2 topological insulators when we add disorder, and I'm going to convince you this is a very realistic, experimentally motivated question with data. Okay, so let me just start by thanking my collaborators. Longtime collaborator Justin Wilson, who was a period of time my postdoc, and now to LSU. We've written a very nice review, in my opinion, a nice review on this topic. So, a lot of the papers I'm going to discuss are in here, and the most recent thing I'll present is in this archive posting. But to talk about this posting, I realized I need to really take you through the background. Okay, so I'm going to try to make this somewhat complete, though of course I'll leave a lot of the details, hopefully. Conceptually. Okay, so let me tell you where I'm taking everybody. So I'm going to give some overall motivation, background to this question, why do we care? And that's going to bring us to the question of understanding stability of Dirac and Weyl semimetals in 3D, presence of disorder, and I'll be thinking about non-perturbative effects of disorder, so-called rare regions of the random potential. Once we understand this solution, we can come back and apply this to here, though we have to work quite a bit harder, because we have to involve transport quantities as well to make the full conclusion. Okay. So there's a very nice previous two talks, so a lot of this has already been introduced, so let me just kind of go more quickly. So we have same bulk insulators in 3D, and we're thinking of these to be non-trivial Z2 invariants, such that I have edge modes that are protected that live inside that bulk gap. So for example, here's angle result photoemission spectroscopy data on, I think, bismuth selenide, I want to say, where this is the surface Dirac cone observed on the surface of the material in experiment. Yeah. So this is one way you can just grow these materials. Another way we've learned to realize these materials, these topological states, is via doping a strong spin-orbit insulator. So you identify a strong spin-orbit insulator, and you dope it with some other material to basically invert the band gap. Okay. So you can take a trivial insulator and make it topological. But that doping is going to do something much more non-trivial, and that's going to be a big focus of what actually is going on in an actual physical system. So let's think about this mathematically. So our 3D TIs are described by a massive Dirac Hamiltonian, which I've written in some continuum language. Okay, and so just to be very oriented to everybody, we have 4-component Dirac spinners. Here's our 4x4 Dirac matrices. If you remember from relativistic quantum mechanics, this is math community, so maybe you haven't taken such a class, but nonetheless, you've probably seen the equation. And so now what's interesting here is this so-called Wilson mass or k-dependent mass, which should make this topologically non-trivial. For a positive B parameter, positive n makes this topological. And you can compute this if you put this on a lattice via these parity eigenvalues at the trim points, as just being discussed a second ago. And this can be topologically trivial in the other regime. And I might be switching my definitions of M throughout, so I apologize if I do that. But here's our phase diagram. Okay, so doping is going to tune the mass gap. It's also going to introduce disorder. Let's ignore this second statement first. Let's just think about tuning the mass gap. Okay, so if I tune the mass gap, I should be able to go from a trivial phase where my surface is gapped to a topological phase where my surface has a Dirac cone. Okay, so here's an experiment where you see the doping changing. You see that on the surface, the gap closing, you get this topological phase. Okay, so the question is one major question here is this a sharp transition? Okay, that's going to be a big question. And if it is sharp, let's just assume it is. I go with that. If it's sharp, then there would be some sort of Dirac semimetal sitting in the middle. So that's certainly rigorously true if I ignore the effects of disorder. If I just vary this mass parameter, I go from topological to trivial, But the major, and you can actually prove. Oh, that didn't. Okay, so that didn't make it. So some things didn't make it into PDF. Let's see. Yeah, so these a lot of file figures aren't surviving in my convert. Can I connect my computer or something? It's a relatively small group of us here. There's just a bunch of things that are not like there's a whole.
Know how to do that.
For example, there's like some pictures
Change
that aren't making it.
Perhaps.
Send it again, maybe.
No, copy it here to a USB drive. That's easier.
Sorry.
And then no. And I don't know.
With my computer.
And share screen.
And share your screen.
Yeah. Okay.
Oh, that's even more difficult.
Okay. Okay, Bernardo.
One thing. But I don't know how to change it.
Yes, it's weird because here I even have.
You could try. There is a cable here, so
It's just not rendering on the.
We can put here.
We think the PDF is stable.
But maybe you
Can I
can
connect?
connect to this.
I suppose I don't know what are we projecting.
Is
So
there a Zoom link?
there is a Zoom link on the webpage, but here is the PDF. Look, in the PDF you have the things.
Yeah, that's but that's what I'm looking at my PDF, and it's not what's showing up here. Look, like I have.
Here's the PDF. So
Yeah, but look.
oh, what's going on?
See, all this stuff is not.
Why didn't it come?
And that's the same PDF.
We could either try to connect, or we can either copy it.
Let's try.
Oh, but you don't have this thing to.
I do. I have a newer.
Oh, Natalia.
Yes, what's happening?
It's just the PDF is not rendering.
Could we project this in the screen? Could we?
Yeah, you could run
just-
Zoom on your end.
Okay, do that.
Yeah, and then you can share your screen.
Okay, let me go on Zoom.
Wait, what happened though? Was it not
Like the PDF is not showing up properly.
It's not working there. So
I'm not exactly sure why. Where do I find the Zoom link?
on the website? You can go on insta.miami
About this?
and there, Zoom link. So then I'll make
Okay.
you.
All right.
And then you don't join audio.
No, just X.
Mhm.
Can change.
Yeah, and then I'll make you co-host. Okay.
Let's just get my actual. Okay.
Yeah. And
Okay. Very good. So slides are working. All right. And let me move my.
then you have to do it with
That's okay.
you,
I usually leave these at conferences, so I never have them. This is good. Yeah.
okay.
I just move my computer so it's not gonna fall. This is good. Cool. Okay. Sorry for the technical difficulties. So the point I was trying to make here is that in terms of these topological insulator phases themselves, if I have electronic gaps, these are stable, and you can rigorously prove this, as Emil's done on several papers. But so we're interested in the stability of this Dirac semimetal line where I do not have that electronic gap protection. Okay. So in reality, if I think about this experiment, what's actually happening? In addition to closing the gap, I'm introducing random, basically potential scattering for the electrons in the material, and so I'm going to introduce disorder. That disorder is going to drive you through this phase diagram in some particular cut. Okay, and so for this to be an actual critical point, it requires this point down here to be stable to the presence of disorder. Okay, and if that were to be true, then there would be some sort of tricritical point up here. Okay, and people thought about this originally with theory. You can put this on a lattice and try to do numerical simulations. We'll come back to this several times, but this is one way to put this model on the lattice, a simple cubic lattice. And then you'd introduce disorder with some random potential. And if you're doing finite size simulations, you can fool yourself if you take random potentials that suppress certain physical effects. And so what was initially done was bounded disorder distributions, which can unfortunately hide non-perturbative region effects on small finite size simulations, which was done here, for example, 9 cubed, small. And nonetheless, what you still see is you can do perturbation theory, which gives these black lines, okay? And you can do numerics, and it seems that they seem to work. It seems like perturbation theory is doing a reasonably good job. And you can look here and you see this Dirac semimetal line. It looks like I have a stable Dirac semimetal line. Okay. So this was some years ago. And so then people said, okay, then if that's true, I should be able to study this tricritical point, which may be there, okay? And what they see is then the density of states would be 0 because you're semi-metallic, and then it becomes metallic, and so it would lift off. And so it looks like a transition of the density of states. Okay, so this is really the main question of the talk. So if that's all true, then we're done, and this is the picture, okay? But I'm here talking, okay? So it's not a solution. And what I'm going to convince you of is actually this Dirac semimetal line is unstable, and there is no sharp point separating these two phases in the presence of disorder. In reality, there is a metallic phase that's going to penetrate all the way down to weak disorder. Okay, so that's what I'm going to try to convince you of. But first, let me go through the stability of the Dirac semimetal line itself. Okay, and this takes me back to my postdoc and some work that I did then, and then since then, actually. It's a good problem, so it doesn't go away. So let's put this in pretty concrete terms. So when we say the semimetal is a stable phase or not, what we're saying here actually is this density of states, which is pseudogap-like, remain non-zero, or does it become metallic? That's the question we're asking. Okay. And people asked this question a long time ago. Actually, Eduardo Fradkin asked this when I was 1 year old. In 1986, okay? And he didn't even know about any he was hoping semiconductors one day would have band structures like this. But nonetheless, you can take such a model, okay? So here's I'm taking just a single Dirac cone in the continuum, adding this potential, and you can then do self-consistent perturbation theory in this disorder strength. It's also known as self-consistent Born approximation to derive a self-energy of the single electronic Green's function. Okay, so in physics terms, the imaginary part of this object is going to be inversely proportional to lifetime. Will be related to that density of states being non-zero or 0. So you can solve this self-consistent equation for that self-energy at 0 frequency, and you find a critical disorder strength, where if the disorder is weak, this imaginary part remains 0, meaning the density of states is 0, and if it's big, it becomes non-zero. Okay, so people thought, as Eduardo pointed out, that there should be a phase transition between a semimetal and some sort of diffusive metal when the density of states becomes finite. This lifetime becomes non-zero. So you're inducing a lifetime for scatters on the Fermi surface. It's just exotic that this is ever stable, actually. How could this be stable? And let me just compare this with a normal metal to orient everybody to what you'd be thinking if I just gave you a standard metallic system in 3D. Well, there's a finite density of states, and so it's just going to be a diffusive metal. There's no notion of something at weak disorder. And at large disorder, on the order of the bandwidth, you'll Anderson localize these states because of basically random fluctuations in the energy landscape. Okay, but what Eduardo was saying is that basically there should be this semi-metallic phase down here, which is potentially new, and this density of states at 0 energy is like an order parameter for this potential transition. Okay, so that seemed well and good. Actually, sorry, before I go on, you can actually do more. You can do RG. So you can do perturbative RG 2 plus epsilon expansions. I don't know, mathematicians also are doing RG, right? Doing RG, right? Very good. So probably more rigorously than we are. So so here's a 2 plus epsilon expansion. And so you can basically do this in 3D. So you apply epsilon equals 1. and you find a critical disorder strength that's perturbatively accessible. But what's really interesting, you find these critical exponents, which is basically giving you some sort of non-relativistic critical point, even though you started from relativistic electrons. Okay. And what's also quite interesting is this appears in the density of states. It's not like Anderson localization that appears in the wave functions. And so this predicted a thermodynamic phase transition. And that was quite exciting at the time because you thought you'd have some sort of toy model. You could really study a itinerant quantum critical point driven by disorder. And so this is naively what we thought, as I was saying, this would be some sort of metallic quantum critical point driven by disorder. But this is then raised, what about these non-perturbative effects that everybody has been ignoring? And let me take you through this argument qualitatively, and then I'll give you some math to back it up. Okay, so let me think about non-perturbative effects. So what if I was sampling not a bounded distribution, but let's say something like this, such that it doesn't happen quite often. You can also cook this up for a bounded distribution, which is a little bit more of a complicated argument. But take an unbounded distribution such that locally I can have an event where that potential samples very far out in the tail of the Gaussian, so it's like 5, 6 sigma event. Okay? So this is a very strong fluctuation of the disorder strength. It can be very large. This can happen in materials, happens all the time, with the observable effects, for example. And what happens is you can't do perturbation theory because this part is so large. No way you can do perturbation theory. So everything I was just telling you was one particular saddle point was perturbation theory about the free limit. So we have to do some sort of non-perturbative treatment. And so the intuitive picture is to imagine this is like a scattering event, okay? And we're going to solve the Weyl or Dirac equation for scattering off of such sort of basically a scattering well. You can treat this region as some well, some potential well, some depth, okay? And what you find is there's actually a non-perturbative bound state solutions for so-called magic coupling constants, and those give rise to these so-called quasi-local wave functions, if you were to find such a resonance. And if you then look at all these, if you then add these up, what you find is that at these bound states gives you a finite contribution to the density of states, albeit exponentially small, but non-zero, okay? So this invalidates everything I just told you with perturbation theory. The fundamental assumption of perturbation theory is that this is zero, okay? So this is a different perspective. And here's how you can kind of rigorously derive these things. In the math community, I'm hoping I can provide a little more detail than I normally would for my physics colleagues. And so what is done here is basically treating it as an instanton computation. It's not perturbative. So you basically write down a saddle point equation. This is normalization of a wave function. Here's your Schrodinger equation. And you can then do basically the average over disorder with some kernel, which characterizes the disorder spread in real space and strength. And upon doing that, you get some self-consistent nonlinear Schrodinger equation that you can solve self-consistently, and its solution can be plugged in to find a change in the density of states. So these instanton solutions are going to shift the density of states. These bound states, as I was intuitively arguing, are going to contribute to a finite density of states, the Fermi energy. So you can solve this differential equation for these 3D plane waves asymptotically. You can't solve it exactly, but the asymptotics are sufficient because indeed you recover right away that 1 over r squared solution, as we were expecting from the bound state arguments. And but you have a core to this wave function. So if you integrate that core up, you get a finite contribution, which gives you precisely this exponentially small contribution. So there's an instanton derivation of the non-perturbative effects. Okay, so I'm leaving you right now. We're at a crossroads. So I told you basically this perturbative treatment of the disorder is getting expanded at the free limit, and you find it's perturbatively irrelevant, and you think because you found this irrelevancy, there should be a phase transition out of that phase. The other way we did it was we said, well, there's also these rare events that are inherently not perturbative, and those are going to give me quasi-bound states that I cannot do perturbation theory about, and as a result, I can get a finite density of them that gives me a finite density states of the Fermi energy. So how do I reconcile these two pictures? Okay. So is there any questions maybe before I keep going? All right, great. So to answer this question, you obviously have to do it exactly in some fashion. So we're going to do it exactly on the computer, and we're going to get to really big sizes using tricks such that we can converge things on the computer. Okay. And we're going to do this for this lattice model. So, and I'm going to come back to the 3D TI once I understand how to do it here. Okay. So we have a 3D cubic lattice model for Dirac semimetal. So for example, my dispersion, I have 8 Dirac points at the time of Wilson invariant momenta. So it was a while maybe here. Sorry, goes back and forth. And I'm going to put in a Gaussian disorder distribution as I don't want to artificially suppress rare events. And we're going to focus on this density of states for this part of the talk. And I'm just defining this because you can also just directly compute it. It's important physically. What does this mean? It's our number of states per volume per dE. It's just the distribution of eigenvalues, okay, of the spectral quantity which is the Hamiltonian. And we're going to do this. The trick I'm going to mention is this so-called Perennial polynomial method. It's a computational physics approach where instead of doing exact analyzation, we're going to do a Chebyshev expansion of our spectral operator that we want to compute. Okay, so and mathematicians love Chebyshev polynomials. The more I get to know, at least computational mathematicians do, and they have very powerful properties. And so because it relates to Fourier transforms, and so yeah, it's quite powerful. So the idea is you need to be able to use them, though, you have to get the eigenvalues between -1 to 1. You can do that efficiently via a Lanczos estimate of your maximum eigenvalues. Upon rescaling, you can now expand the spectral quantity, which is our density of states of interest, and you get this final result as I'm showing here. These are just an a priori object that are used to suppress Gibbs oscillations because we truncate this infinite series to finite n. And this is where you actually have to compute something. These coefficients can be computed as a trace of the Chebyshev of the Hamiltonian, which you can do using so-called stochastic trace estimators from computer science. And this has converted the exact analyzation to a matrix vector operation. Okay, so we never do ED. We only do matrix vector operations. Our Hamiltonian is on the lattice. It's sparse. So matrix times a vector gives you back a vector. Okay, and so you can do systems like 200 cubed, for example. Okay, as we'll talk about later on. Okay, so summarizing, we traded off ED for matrix vector multiplication, and the sparsity is why this is useful. Okay, so let me just show you some data. So here's the density of states as a function of energy, different disorder strengths, and it looks like we have a transition. If I plot the value at 0 energy, indeed it looks like at 0, and it looks like it lifts off. You can say, what's the finite size effects down there? Oh wait, sorry, before I even get there, sorry. Let's try to look at, so it looks like I have a critical point. There's this perturbative RG. Let's try to analyze our data within this perturbative RG prediction. Let's see how good it worked, okay? And surprisingly, you find it works quite well. So there's this prediction that Z should be about 1.5, 1 plus epsilon over 2 within the epsilon expansion. One loop, no reason why one loop should work well. But indeed, if you look at the numerics, without looking too carefully down here, but if you look here, you see a very clear linear scaling, which is pretty close to the RG prediction. Okay. But now if you look carefully, so if you zoom in here, you can see there's a very large finite size effect in the data, though it's going down with L. So you're thinking initially, okay, is this fine? These large finite size effects are consistent, but in reality, there's a converged signal, as I'm going to show you down below. And so what was I seeing there? So if you doing numerics and you're not being too careful about where the states are coming from, you have periodic boundary conditions, you put basically a bunch of states right at 0 energy, which puts a huge finite size effect. And so you can, of course, get rid of this by doing a twist of the boundary conditions, okay, which is just a boundary condition. And it's basically threading a flux, which does not produce a magnetic field through the 3 torus. And as a result, you get a finite size gap. Okay, so now we have no states at 0 energy in our finite size simulation. You can now ask, do states appear down here due to these rare events? Okay, so that's the idea. And we're going to basically, we can do this a couple different ways to get eigenvalues and things like that. Let's do something like Lanczos, okay? And we'll come back with KPM in a second. And I'm just going to look at the 4 lowest eigenvalues. So the distribution of these eigenvalues are an estimate of low energy density of states. So here's like my first perturbative state that I moved away, and here's this tail that I was searching for, okay? And here's that second state. because I'm doing h squared to get these, and we're looking at positive energy. I didn't specify that. But what's here is you see these peaks. This is finite size effects, and you have this tail in the background. These are the rare states. Okay, how do I convince you of that? Let's split it up. Let's think about at weak disorder and finite size. I can kind of think about peaks and background. Okay, then as I increase disorder, this distinction is no longer clear. And I'm just reminding you where I thought this critical point was. So let's take a state in the peak. If this is basically, this should just be described by perturbation theory because disorder is irrelevant. So we just do good old perturbation theory. You do the numerics, and indeed you find a plane wave-like state, very spread out. Okay? Now let's take a state in the tail. You see a state in the tail, because it's 3D, I have to do a sum. But you see it's very localized around a region, and I can look in my disorder configuration. You see that's a 4 sigma event. So that was a rare event, and I get this quasi-localized wave function. You can look at how it's localized. Indeed, it's power law-like, agreeing quite well with this prediction. Okay. You can even find samples with multiple rare states. They start tunneling between them, and this is going to allow DC transport to be finite. This should be metallic. Okay. So then you can ask, is this tail L independent? Do I actually get a finite density of states in the thermodynamic limit? And indeed you do. Okay. So you converge this tail. The tail is L independent. That's an estimate of our low energy density states from these rare regions. You can also do this with the KPM. Okay, so we have two different ways of estimating it. I don't want to dwell on it too much, but you can put them together, and you see it follows this exponential form over about 5 orders of magnitude, fitting this quite well. Okay.
Excuse me.
Yeah, go ahead.
I'm sorry, I'm a little lost. So the rare states are localized in momentum?
Quasi-localized in real space. So this was a plot in real space.
I see.
So this is a quasi-localized in real space. Yeah, so the plane wave was the perturbative state. It gets like kind of bound to this really strong disorder. It's like a bound state.
Around the
effect. Exactly. Just like a bound state in quantum mechanics. It's just for this Dirac equation. That's like the toy calculation you can do to describe it. Very good. Okay, so now you can put this together. So this is where I was showing you data before. Look at this, everything's converged, and it goes well below it, orders of magnitude below it. Okay, so this is where people thought we were just seeing a finite size effect. So this is maybe a word of caution for everybody who does numerics. You know, you might have a converged exponentially small signal down below. So be cautious with rare events. Okay. So what happened to this quantum critical point? Because I showed you data that seemed like agreed with this RG. What's going on there? And this is like an empirical proof by contradiction. So if there is a quantum critical point, this density of states is a non-analytic function at the critical point. But let's assume that's not true. So if I assume that is not true, I can just Taylor expand my density of states. Okay? And then this will diverge if my assumption is wrong, because you can relate this to a correlation length, right? So this correlation length diverges if it's actually a true phase transition, and my assumption would be completely incorrect, okay? So I'm going to put this on the computer, I'm going to scale it up, and I'm going to ask, does rho double prime diverge? And the answer is no. You can go up 131, it barely changes, and it's very nicely converged, okay? The density of states remains an analytic function. There is no transition, it becomes a crossover. So these rare events,
independently of the dimension of the system. So this
independent of
is
the system
3D.
size, independent of this is all 3D, and this is like, imagine the thermodynamic limit. So the statement is, in the thermodynamic limit, there is no phase transition. Yes.
Is there a reason why we pick the whole numbers?
That's just like because that's the no real reason, just a quantitative reason. So you have Dirac points at the time of invariant momenta. If you choose odd L, then they're all kind of not right at zero energy, and you kind of, anyways, we're averaging over these twisted boundary conditions, you get better. You average better, but it's just a technical thing. There's no real reason. Okay, so let's put this together. So this is this Dirac semimetal line that people thought was stable, and we thought there was a critical point, but in reality, it's not. So this whole thing is a diffusive metal, just like a normal metal. we didn't induce a finite density of states down here. This became a crossover, and this quantum critical fan we thought is a crossover diagram. And so physically what's going on is there's a correlation length, which is much less than this exponentially large rare region length scale. And so it looks quantum critical until that length scale, you get close enough to where you think this putative transition is, where you really realize that this exponential length scale that never diverges. That exponential length scale is being set by these rare bound states. Okay. And so we say this critical point's hidden, and we can demonstrate this in a wide class of systems. So you can break time reversal, you can consider, I wanted to mention just so you know, charge, systems that have charge conjugation are superconductors. So there's a large class of systems on your table that have particle symmetry. And also you can take random hopping, that's another one, for example. Or the single Weyl cone, which you can actually realize on a lattice, but you can try to look at these properties. And so this is not a property of other Weyl cone scattering. This is an effect from these rare region effects. And so there's an initial theory. So I'm bringing this up because I think this is an open problem. I mean, in field theory, nobody knows how to describe what I just told you, these two different dichotomies. We have numerics that has explained it, but there is no transition. So Victor Guerrari made an attempt, this I'd say is a first go at trying to develop a theory for this avoided quantum critical point, but I bring this to everyone here because I think maybe somebody here can maybe figure it out. And so the idea is he took a gas of instantons, just like I showed that could have multiple rare events, and what he's able to show is that you get a Coulomb gas, and that Coulomb gas he was able to basically treat at mean field level and show that that correlation length is then cut off by the density state. So he showed analytically what I was arguing on the previous slide in a pretty simplified calculation. So he ignored a lot of the details, and it was all kind of phenomenological. So, I think this is very much an open problem. I'll put this to all of you. Okay. Okay. So just before I go back to the 3D TI problem, I just want to tell you that you cannot get rid of this avoidance. So how can you tune the avoidance? So can we try to suppress these rare regions by changing the distribution? So can you get rid of them? And the answer is going to be no. But the idea we had is maybe it's all about these tails of the Gaussian. So what if I can really try to suppress these tails, and I can do that by taking a bimodal distribution. Okay, this bimodal distribution is like two Gaussians where I vary their mean and their width. Okay, and I can now use and this is just conceptual, a rare state is going to become was localized, can be very spread out in this new configuration. And so now let's look at this rotable prime. So as I argued, this rotable prime tells me how strong how strong the avoidance is. So if rotable prime is very small, it's really strongly avoided. Okay, this is a Gaussian disorder. That's what I showed you a couple slides ago. I now start tuning these tails, and you can see that avoidance is getting weaker. The criticality is becoming stronger, and all the way binary, we never can converge this peak on finite size simulations. And over like 2 decades of data collapse, you can see critical properties. So it's like you can, there is some sort of critical point in the spectrum, but it's always rounded out. And that rounding out scale you can make very small. And so basically the picture here is you can tune this scale, but if you have rare events, there's no way to get rid of it. And if you like number theory, you might know that quasi-periodic potentials are like twists, like Emil was describing. Quasi-periodic things have no rare events, but they have energy level detuning, and you can actually get a true quantum critical point if you replace the random potential by a quasi-periodic one. But this is an entirely different talk, and this is also related to magic angles. This transition is related to the magic angle. You can relate it in twisted Euler graphene in one lower dimension. So it's all pretty much connected, turns out. So we have a paper on that as well I'm happy to talk about. But as I said, it's a completely different talk. So let's come back now to the TI phase diagram. So while I could have ended here and said, I showed that this point is unstable, everything I focused on was on a semimetal line, and now in reality you have insulating phases on either side. And so you have to actually identify a metallic phase of finite extent. It's much more than we've done, but we now have the tools to do it, and you need to also compute transport. So can we actually demonstrate this? That was the question, okay? And this took several years of effort, and I'm very happy to complete it. And so let me tell you about our efforts to do this. So as you can see, it took several years. Yixing's now in the real world, and I developed a lot of machinery, and it took a lot of time. So we're back to this lattice model, the 3D TI, and now we've learned we're not going to take that bounded distribution. We're going to certainly take a disordered distribution that allow these rare events to be seen easily on the simulations. So here's data. So let's look at these analytic properties of the density of states. So this is a color plot of the density of states, disorder, here's your mass, ratio of masses. So here's my trivial phase, my topological phase, okay? And we can identify this line that I was sketching for you. We can really identify it. And here's this avoided transition. So how do I see all that? Well, I see that by looking, now I can look along this line, right? And indeed, I see this exponentially small density of states from these rare events all along this line. Fits quite well. And you can then also look at rotable prime, and you can see that rotable prime is very nicely converged, okay? So you have this avoided transition up here. But as I said, we have close proximity to insulating phases, and so the density of states now is not enough. Okay, the density of states in principle can always be non-zero in an insulator because of rare events, but those wave functions have to be extended. Okay, not localized. So you'd see that by computing the DC conductivity. To do this with this KPM method is complicated, but as pointed out here, you can use GPUs and you can really ramp it up, and so that's what we had to do. And you can see this is the large, this is not so large yet, but it'll get really large for the simulation. So here's now the conductivity, okay, color plot. And here's where that avoided transition was. It's looking much more like my cartoons, right? And you can now look at this prediction of this criticality at finite energy in the conductivity. So this prediction for this avoided transition would be at finite energy, I should see an energy scaling, which is 1 over z, and that's this dashed line. So we have this energy scaling at finite energy, but down at low energy, it rounds out. And the question is, what's going down at low energy? You know, it's at zero energy there at the Dirac node. Here's the conductivity following this rare region form. This is the first demonstration of this, as far as we know, and it goes beyond the previous theoretical predictions. Exponentially small conductivity. And the reason why it goes beyond is because it's inherently non-perturbative diffusion. So it's quite interesting in terms of just transport phenomenon. So you have a density of states, you have a conductivity, I can define a diffusion constant, right? It's just a ratio. Well, if you do a perturbative argument, you would argue basically the wave, the time, so the diffusion constant is like x squared over t, and the time to tunnel is, like 1 over the wave functions, which is going like, or 1 over squared, so that basically cancels, and so your diffusion constant should be disorder independent. Sorry, I should have done the slide a little more clearly, but that's not at all what we get, okay? So perturbation theory does not fit this data in any way, and this diffusion is inherently non-perturbative. This is an additional open question. I don't even yet know how to describe this theoretically, and it's something we're starting to really think about carefully. Okay, so as I said, I have a challenging task to show you there's actually a metallic phase sitting between the two as my last thing I want to do. And so how do I do that? I'm going to use a combination of the wave functions in addition to the conductivity to map out these phase boundaries. And so if you're familiar with Anderson localization phase transition, the wave functions develop something known as multifractality, which basically means that the critical exponents are actually changed as I change this power q in this sum. And since it depends on every q in a nonlinear way, it's so-called multifractal. And this alpha q is a way to compute this multifractal spectrum. So this is a very nice paper, if you're interested in this approach, where they pointed out that this object has no spare scaling dimension. So if you study localization, you might use this inverse participation ratio as their scaling dimension, another fit parameter you have to determine. So this doesn't have that. And so it predicts that if let's say I take a Q around here, on one side it's insulating, on the other side is metallic, and criticals between the two. And so you can predict a scaling function with no scaling dimension, and so the data should exhibit some sort of crossing at the transition. So let me show you this data. So here's going through this either topological or to metallic phase or trivial to metallic phase. And you can see that there's a crossing, that crossing is drifting. So these are different system sizes. But the estimate of the crossing is an additional estimate of the localization phase boundaries. So we have conductivity, we have wave function properties, and then you can take a horizontal cut way down here, well below this putative putative tricritical point, which is showing you avoided transition. And you see clearly two transitions. Okay, so this is pretty far down. This data took a long time to generate, a lot of samples. And indeed, you see very clear evidence of the metallic phase. And these crossings are not drifting inward, they're drifting outward. Okay? And so it's really showing evidence of this metallic phase. So if you put this all together, these are just like lower bounds, but this is actually pushing outward in that scaling theory, but this is a lower bound of the estimate. Okay? So indeed, we've identified basically several different metrics that show there is this metallic phase. So the wave functions are providing a lower bound. There's certainly nothing in between them. It's pushing outward. And so I hope that is clear. So I can just end here a little early. But basically, I've taken you back through the fact that rare regions destabilize semimetallic phases in 3D. It leads to the absence of the semimetallic line. And this is a property of any topological insulator in 3 dimensions, is what I'm arguing, due to disorder. So any real material will always have disorder. So if you ever try to drive such a transition, an experiment, there's a big difference between doping and pressure. Okay, pressure will not do any of these effects. It's just whatever intrinsic disorder is there will be there. But with doping, you're really driving the amount of disorder. So thank you for your attention, and